going to go over the rest of chapter 23 and start some problem solving. Okay. So remember last time we said there are particular situations where we can use Gauss's law in order to solve for the electric field. Okay. And usually when you have a symmetric charge distribution, either you have a spherical symmetry, like a pointed charge, a sphere, a shell, that has a spherical symmetry, you can easily define Gauss's surfaces, Gaussian surfaces, and be able to determine the electric field. As we have seen, we did it for a full sphere with uniform charge distribution. We did it for a sphere that is a conducting sphere that has all the charges on the surface of the sphere, and we did it for a point charge. Okay. We also did it for a line charge, and in this case we have cylindrical symmetry, and we defined the surface, a cylindrical surface, Gaussian closed surface, and we were able to determine also the electric field easily. Okay. So at the end we did the same thing for a planar symmetry, and I would like to repeat that because we were doing it towards the last minutes. Okay. But remember, in order to exploit Gauss's law and be able to solve for the electric field, the surfaces of the closed surface have to satisfy at least one of the conditions that we listed here. Okay. So the first condition is E is constant. Okay. On the surface, or a portion of the surface. Another condition is if the electric field vector and the area vector are parallel. In that case, the dot product is just E times dA. Or if E and dA are perpendicular, in that case the flux is 0. Okay. And the last case, if the electric field is 0 over a portion of the surface. Okay. So remember, we did it for a sphere. Thank you, Ibrahima. It worked while it got afraid. Okay. So we did it for a sphere, and we determined that the electric field outside of the sphere, we use the shell theorem. We said outside the sphere you can treat the sphere as if it's a charge with a located at the center of the sphere, as it's a point charge located at the center of the sphere, and with the charge equal to the charge of the whole sphere, and we call that the shell theorem. However, if you go inside the sphere, we use the Gaussian surface, and we solved, and we had to determine obviously what is the charge enclosed in the internal surface, and we found that there is a linear relationship between the electric field and R. So we found two equations. One equation is outside, which is the same as the Coulomb's law, KQ over R squared, and inside the sphere there is a linear relationship, which is KQ divided by the area of the sphere cubed, A cubed times R. So this is a linear equation. Okay. And obviously at the radius of the sphere these two values are equal. All right. Then we did it for a conducting sphere. In the conducting sphere, all the charges are on the surface, and we will study that in the next chapter. Okay. And so if you are outside of the sphere, we use a shell theorem. It's KQ over R squared. So outside the radius, we found that the electric field is just KQ over R squared. So this is KQ. The electric field in this case is KQ over R squared. However, inside the sphere, when we define the Gaussian surface inside the sphere, we determined that there is no charge enclosed. When we did this Gaussian surface inside the sphere, the charge enclosed is 0, because we said all the net charge or the extra charge always goes to the surface of the conductor. Hence, the flux is 0 and the electric field is 0 inside. So if you plot the electric field versus the radius, as long as the radius is less than the radius of the sphere A, it's 0. Okay. When you reach the value of A, suddenly the value jumps to this value, which is KQ divided by A cubed. So here, this is going to be E is equal to KQ divided by A squared. A squared. Okay. Then we did it for the cylindrical case. And when we did the cylindrical case, we found very interesting result. If you have an infinite line of a charge lambda, charge per unit length lambda, we defined this cylindrical surface, okay, and we did the integration. Obviously, the flux through this surface is 0. The flux through this surface is 0. Through the bottom surface, the flux is 0, okay, because the electric field and the area vector are perpendicular to each other. But on the belt of the cylinder, we were able to determine what's the area of the belt, which is 2 pi r times the length of the sphere, or the height of the sphere L. It's equal to the charge enclosed, which is lambda times L divided by epsilon 0, and we solved for the electric field. We found very interesting that now the electric field is not dependent on 1 over r squared, it's 1 over r. Okay, so this is the general equation for the electric field from an infinite line of charge. Obviously, if the line of charge is positive, the electric field is pointing away from it, and if the charge is negative, the electric field is pointing towards it. Okay, obviously in these situations, let's assume you have two line charges and you are interested at a point in between. Let's say there is a point in between here. Okay, so for this point, the electric field contribution from the positive charge, the electric field is going to be like this. So let's call this is 1 and this is 2, E1, okay, and so it depends obviously on r, on the distance r. Let's call this r1, let's call this distance r2. Okay, if you draw the electric field from the negative line charge, the electric field will be in the electric field also E2. This is due to charge tube, and remember the electric field points towards away from the positive charge and towards the negative charge. So you can see in this case E1 and E2 are in the same direction, so they don't cancel. Even if R1 and R2 are equal, the electric field do not cancel in between them. Okay. However, if this was positive and this was positive, then they would cancel. The electric field between the two line charges at the center, they will cancel because the magnitudes are equal and the electric fields will be in the opposite direction. Okay, so last time we did this one, okay, and we said for this one, let me quickly repeat it. Okay, so this is the surface with a surface charge density sigma, okay, and we want to determine the electric field, so we made a cylindrical Gaussian surface. So this is a cylindrical Gaussian surface, okay, so it has a belt and has two sides. The cylinder has a belt and two sides. Okay, we determined that the electric field is always pointing away from the positive charge. So on this surface here, the electric field and the area vector are perpendicular, so the flux is 0. But on the front side and the back side, so let me write this. The flux is E dotted with dA is equal to the charge enclosed divided by epsilon 0. Okay, oops. Okay, and so we divide this by we call this area 1, I think we call this area 2, and we call this area 3 here. So this is equal to the integral of not closed over area 1 E1 dA or EdA plus the integral of area 2 Ed dot dA plus the integral of area 3 E dotted with dA. This is equal to the charge enclosed divided by epsilon 0. For area 1 and 2, you can, let's draw the area vector. So let's draw the area vector. So this one has an area vector like this, delta A, which is let me call it delta A1. It's parallel to the electric field, and here this is delta A2. It's also parallel to the electric field. So when we do the flux in this case, so this is going to be equal to E times the area A. So this is the area A. This area is A here. And same thing for the front is EA plus EA. For the belt, we said the area vector and the electric field are perpendicular. Let me draw vectors. So this is the, for the belt, this is the area vector dA3 or delta A3, delta A3. Notice that in this case it's perpendicular to the electric field, okay, and hence the flux is 0, so plus 0. And we said in order to determine what is the charge enclosed by this cylinder, this is the area that is enclosed, that has a charge. It has an area A. Since we have the charge per unit area sigma, if we multiply it by A, we will get the charge. So this is equal to sigma times A divided by epsilon 0. So we end up with the flux is equal to EA is equal sigma A divided by epsilon 0. The A's will cancel, and we obtained the electric field is sigma over 2 epsilon 0, which is quite interesting because it does not even depend on the distance. So remember, for a point charge, the electric field is kq over r squared. For a line charge, infinite line, we find what was it? It was E was 2k lambda over r, and now for a surface, an infinite surface, we're finding E is sigma over 2 epsilon 0. It's telling us that the electric field is constant from an infinite line, infinite surface. It's constant, and it's not dependent on how far we are from this plane or from this charge. So it's quite, it might be counterintuitive, but you can check the math and the physics. So this is the electric field. All right. All right. So this is the result, the final result. Okay. And so here we are looking at the cross section. Obviously, because we have positive charges, the electric field is always pointing away from the positive charge. But if this was a negative charge, then the electric field will be pointing towards it. Okay, so let's take the next example. Okay, so here suppose two infinite insulating planes of charge are parallel to each other, one positively charged and the other negatively charged. Okay, the surface charge densities of both planes are the same magnitude, so let's call them the sigma. Okay, what does the electric field look like in this situation? So we want to determine the electric field. All right, we have an equation for the electric field, so let me start with this one. This is 1, this is 2. Okay, so the electric field from 1 is pointing away from the positive charge. Okay, so I take any point, for example. Oops. Okay, so this is E1. Okay, and we said it's sigma over 2 epsilon 0. Okay, and it's in the positive direction, so I can write, if I want to do it in vector notation, since this is the x position, this is the y position, for example, I can write that actually E1 is equal sigma over 2 epsilon 0 times I. This is unit vector in the x direction. Okay, let's look at E2. E2 is due to the negative charge, so in this case also the electric field is going to be pointing towards the negative charge, so E2. So E2 is also sigma over 2 epsilon 0, and so I can write it also in unit vector notation. E2 is sigma over 2 epsilon 0 I. So if I add them, E total, which is E1 plus E2, what do we get? We get sigma over 2 epsilon 0 plus sigma over 2 epsilon 0. So that will be sigma over epsilon 0 I. This is a superposition principle. We said if you have multiple charges, you can determine the electric field from each charge distribution. So here we have two charge distributions, two infinite planes. We get the electric field from one, we get the electric field from the other one, and we add them. Superposition principle. All right? So this region, notice that it does not depend on the distance. So any point you take here, any point, the electric field is always sigma over epsilon 0 I. So it is a uniform electric field between these two infinite planes. Uniform meaning the electric field has the same direction and it has the same magnitude. This is an example of how we can get a uniform electric field. So if you have two infinite planes, one with charge positive and one negative, you can have a uniform electric field between them. And the value of the electric field does not depend on the distance, between the two. Okay, now how about outside these two planes? So let's take a point here. Okay, so let's do the same thing. Let's draw, so if I want to determine the electric field due to the positive charge, it's away from the positive charge, so this is E1. Okay, how about the negative charge? The negative charge is going to be E2. And notice what happens here. They cancel. The electric fields, they cancel. So to the right and to the left, same thing. And to the left of the planes, of the charged planes, E1 plus E2 is actually equal to 0. So the electric field in this region here, so we can say in this region the electric field is 0. In this region also the electric field is 0, and in between the electric field is equal to sigma over epsilon 0. Very interesting, huh? You get two infinite planes, and because the electric field does not depend on the distance from the plane, the electric field between them is uniform, but outside them it's 0. That's what makes a capacitor. A capacitor has two parallel plates. When you establish a voltage between them, you have an electric field inside the capacitor, almost uniform electric field, but outside the capacitor the electric field is 0. So this is a very nice example. Okay, so this is the superposition principle. E outside is 0 and E inside is sigma over epsilon 0. Let's do one more case before we start solving some problems. So this one, we have a figure. It shows in cross section a plastic spherical shell with a uniform charge Q minus 16E. So this is Q minus 16E. This is a shell, and a radius R equals to 10 centimeters. So this is radius R. Okay, a particle with a charge 5E is at the center. So this is at the center. Q is 5E at the center. What is the electric field, magnitude and direction at point P1? So this is point P1. It's between the charge and the shell, and also at point P2. So they gave P1, it's a radius R 6 centimeter, and P2 at a radius R2 that is equal to 12 centimeter. So this is again, this problem we have a spherical symmetry, so we can easily use Gauss's law in order to solve this. Okay, so what we will do, we define closed surfaces at those points. Okay, so let me start with the P1. So for P1, let me do a Gaussian surface. So this is a sphere of radius R1. Okay, so point P is on that sphere, and let's use Gauss's law. So Gauss's law says the flux is going to be the integral of E dotted with dA is equal to the charge enclosed divided by epsilon 0. Okay, so since this is a symmetric situation, the electric field, so this is 5E, it's a positive charge, so the electric field is going to be always pointing away from the positive charge here. Okay, and it happens to be parallel to the area vector. If you draw the area vector is always perpendicular to the surface, so this is the area vector, and it's parallel to the electric field. So now we can simplify the integral. This is just equal E of the area dA. What is the charge enclosed by this sphere, by the internal Gaussian surface? What is the charge enclosed? You can see it in the figure. What is the charge enclosed by this red spherical surface? Q. Why are you hesitant? There is no other charge. There is only Q. We said the Gaussian surface, the Gauss law says the flux is equal to the charge inside this closed surface divided by epsilon 0. The only charge inside the surface is Q. So it's Q divided by epsilon 0. So the integral of dA is just the area of the sphere. So this is E times 4 pi r squared. This is charge enclosed divided by epsilon 0. And we get E is equal 1 over 4 pi epsilon 0 Q over r squared. We could have used the shell theorem even for this, I mean, this is a charge. So this is equal, KQ divided by r squared. Okay, so this is for point P1. I can replace, this is R1, so I can place R1 and determine the value of the electric field. Let's do it for point P2. So for P2, we have to define a Gaussian surface that contains P2. So this is my Gaussian surface. It's a sphere also that contains point P2. And I'm going to do the same thing. The flux is E dA is a charge enclosed divided by epsilon 0. And since it's the same situation, from the symmetry, the spherical symmetry, the electric field vector and the area vector are going to be in parallel. So this integral simplifies to E times 4 pi r squared, E times 4 pi r squared, similar to this case here, is equal, what is the charge enclosed now? What's the charge enclosed? Q plus small q plus capital Q. So this is Q plus capital Q divided by epsilon 0. So what is, so small q is 5e and large q is minus 16e divided by epsilon 0. So we get the electric field times 4 pi r squared is equal minus 9e divided by epsilon 0. And I can get the electric field is equal 1 over 4 pi epsilon 0 times minus e, let's see, minus 9e, minus 9e divided by r squared. So this is equal to minus k times 9e, which is the charge, small q, 9, not q, this is 9. 9e divided by r squared. So notice the electric field now is pointing in the negative direction. So the electric field here, because of this minus sign, it's pointing in the other direction. Why? Because the total charge, small q plus capital Q, is a negative charge. So the total charge is negative, which is minus 9e. Hence the electric field is pointing towards the center of the sphere. Okay, but the magnitude is k times 9 times e divided by r squared. So you can see this is a situation where we have a spherical symmetry and we were able to solve for the electric field inside and outside. Okay, that's it's simple, straightforward. I'm going to leave this example to next chapter, because we are going to be speaking about conductors and the fact that the electric field inside a conductor is always 0. The electric field inside a conductor is always 0. We have not spoken about that yet. We will introduce it in the next chapter. Okay, so now let's solve some problems from this chapter and think about it. It's preparing you for the quiz, so you're exercising your brain cells. Okay, So here, okay, let me see. Okay, let's play. Start. Okay, so please join the Kahoot, and the pin will appear shortly. Okay, 187-9559. 187-9559. Everybody please join. Okay, so while you're joining, let me skip the first problem because we already have done the first problem. So let me go next, and let me skip this one. Skip. Next. Huh? The pin is 187-9559. Okay. All right. So the scores are all 0 now. Huh? Okay. Next. All right. So how about yeah, 1 minute or 1 minute and a half for this one. It's a warm up. If you cannot read it, let me read it for you. Find the net electric flux through the cube shown in figure. Can you okay, so you're going to answer question A, all right? And question B, I want you to think about it because I'm going to ask you, can you use Gauss's law to find the electric field on the surface of this cube? Okay, so do A, we'll do the Kahoot for A, and then we will try to answer question B, or the second question. All right? Everybody join the Kahoot, please. What is what? The charge, there is 2 charges. One is 3 nanocoulomb, the red one inside the cube, 3 nanocoulombs, and the blue one outside the cube is -8 nanocoulombs. Okay, done? Okay, I'll start the Kahoot. You still have 20 seconds, so you're going to choose between A, B, C, or D. Okay, so let me start. Okay, very good. We have 16 correct results and we have 12 incorrect. Okay, so this is an easy problem. Okay, so here we just use Gauss's law. Gauss's law says the flux is equal to the charge enclosed divided by epsilon 0. The cube is a Gaussian surface, it's a closed surface, and the charge enclosed is 3 10 to the minus 9 coulomb divided by epsilon 0. And in this case, when you evaluate this, you find that this is equal to 339 Newton meter squared per coulomb. One step. This is what we call a single step easy problem. Okay. Now, obviously, this charge here does not contribute to the flux because it's outside of the cube. Okay. The next question is, can you use Gauss's law to find the electric field on the surface of this cube? What do you think? And we found the flux, but can you determine the electric field? How? Go ahead. And somebody said yes. You have to justify your answer if you choose an answer. Yes or no? Yeah? No. Why? Wallahi, you're very far. Okay, so the charge, first of all, is not in the middle. We don't have a symmetric situation. Okay. The trick we played last time, when the charge was in the middle of the cube, we did not use Gauss's technique to determine the electric field. We just used the fact that the cube, the flux through one surface is 1/6 of. In this case, the charge is not at the center, so we cannot play that trick. We do not satisfy any of the 4 conditions for applying Gauss's law to solve for the electric field. We don't have a symmetric situation. The electric field is not constant on any of these surfaces. It's not constant. The electric field is not parallel to the area vector on any of these. The only position is at. So, for example, if you're here, let's say you're here, the electric field is going to be like this, and the area vector is like this. So they are not parallel. Okay, they are not perpendicular over all the surfaces, the electric field and the area vector. And the electric field is not, what's the other 4th condition? 0. And it's not. So none of these conditions is satisfied by all of these surfaces. We cannot use Gauss's law to solve this problem. So usually, to make it simple, we can use Gauss's law if we have either cylindrical symmetry, spherical symmetry, or planar symmetry. In those cases, we don't have any of these situations here, then we cannot use Gauss's law. Next problem. Okay, 58599 leading by a small margin. Okay, so here is another question, and you're supposed to answer question B. So let me read it in case you cannot. Find the net. I wish I had some way of magnifying this, but find the net electric flux through the closed spherical surface in the uniform electric field shown in the figure. So on the left you have a sphere and a uniform electric field. So that's the question A. Question B, that's what you're supposed to answer. The closed cylindrical surface shown in the figure to the right. Okay, we want to determine what is the flux. Okay, so notice here, if you do not see the arrows clearly, the electric field to the right is pointing to the right, and at the other side is pointing to the left, and the electric field is perpendicular to these surfaces. Okay, so answer question B, and you will have 1 minute or 2 minutes. Let me give you 2 minutes to answer this one. So you choose between the A, B, C, or D. Yes? So A says 2 pi r squared E, B says 0. Oh, oh boy. Okay, so sorry, the third one, C, should be 3 pi r squared E. Is it? Yeah, I made a mistake. C is, so it's 3 pi r squared E, and D is 2 pi r E, yeah? So C is not 2, it's 3. Or, I forgot. Okay, never mind. Use 2 pi r squared for C. And I forgot. All right. Okay, so since we have a problem, try to answer it anyway. Choose which one is the correct answer. Sometimes I make mistakes in these Kahoots. Yeah. Okay, so choose between A, B, C, or D, and I assume C is 3 pi r squared E, so we will see which one is correct. All right, so 20 seconds to enter your question. All right, okay, sorry, I said C. So I should have said A 3 pi r squared. The correct answer is actually C. So those who said A, it's correct also, but the score will not be correct now in Kahoot. All right. So let's look at this problem. Where is it? Okay. All right. So first of all, to the left, we clearly see this is a sphere in uniform electric field, and remember there is no charge inside here, even though the problem did not say, but usually if you have a closed Gaussian surface in uniform electric field, the flux is 0, and you can do that. You can count the number of electric field lines going in and out. So the number of lines moving in is 1, 2, 3, 4, 5. The ones moving out, 1, 2, 3, 4, 5. Flux in and flux out, they cancel each other, so the total flux is 0 for the sphere. Okay, for the cylinder, they're showing us the electric field. Obviously, so we can determine. So this is area 1, area 2, and area 3. Okay, so for area 2, since they did not show any electric field and the electric field is perpendicular to area vector, this one gives us a flux of 0. But for area 1, the area vector, let's draw the area vector. This is the area vector, delta A 1, and here this is delta A 2. So flux 1 through area 1 is just going to be E dotted with delta A1. Since they are parallel, cosine of 0 is 1, so this is going to be E times the area, which is pi r squared. Okay, for the flux 2, same thing, we get E dotted with delta A2, and since they are parallel, cosine of theta is 0, cosine of 0 is 1, so this is also E times pi r squared. So the total flux is going to be the sum of the two, which is 2 pi r squared times E. This is the total flux. Okay, what can you conclude about the charge, if any, inside the cylindrical surface? Is there a charge inside the surface, this cylindrical surface, or not? There has to be, because the flux is not 0 through the closed surface. So we can say this is equal to the charge enclosed divided by epsilon 0, and I can solve for the charge enclosed is going to be 2 pi epsilon 0 r squared times E. So clearly, and it's a positive charge, because notice the electric field is pointing away from the inside of this closed surface, so it has to be a positive charge. Okay, clear? Clear? These are important examples. Next problem. Okay, so the scores are going to be skewed now. No, actually, because there were no correct answers, so the scores are still correct. Okay, so for this problem, let me read it. Assume the magnitude of the electric field on each face of the cube of edge L. The edge is 1 meter for this cube. In this figure is uniform, and the direction of the fields on each face are indicated. So you can see the arrows with the numbers. I will read the numbers shortly. Okay, the question is find the net electric flux through the cube. That's question A, and the net charge inside the cube. So you have 25 newtons per coulomb here moving in, 20 newtons per coulomb in the back surface moving out, 35 newtons per coulomb moving in on this this surface, 15 newtons per coulomb down, and on this surface is 20 newtons per coulomb moving out, and this is 20 newtons per coulomb moving out of the cube. So determine, first of all, find the net electric flux through the cube. Okay, and once you do that, that's the question A, then you need to determine what is the net charge inside the cube. Okay, 2 minutes. Okay, ready? So choose between A, B, C or D. This is for question A, which is asking about the flux, the net electric flux through the cube. Okay, I'll start. You'll have 20 seconds. Okay, so we have 14 correct answers and we have 15 incorrect answers. Not bad. Okay, so let's look at the this problem here. Yeah, this one. Okay, so obviously each of these areas of the cubes, the area is L squared, so the area of each of the surfaces is just L squared. Okay, and so we can determine the flux through each of these areas, but let's the total flux. Okay, so remember, if the electric field is piercing into the Gaussian surface, the flux is positive or negative? Negative. Raise your voice, please. If it's piercing out, it's positive, and if it's tangential, it's 0. The area vector is perpendicular to the electric field. Okay, so let's add all the positive terms first. Okay, so the area, which is L squared, we're going to multiply it by all the positive terms. So we have 20. So this 20. We have 15. Okay, and we have another 20 plus 20, and we have another 20 plus 20, and that's it for positive, I think. Moving out 1, 2, 3, 4. Okay, now, and for the negative we have minus L squared. The area is still the same, and so which ones are negative? So let me indicate them by blue color. We have 25 here. Okay, and we have 35 here plus 35, and that's it. We have checked all the so we can say 60 plus 15, that's 75 L squared, 75 L squared, minus 25 plus 35, that's 60 L squared, so that is 15 L squared. Okay, so 15 L squared, and since L is equal to 1, so this is going to be 15 Newton meter squared per Coulomb. So this is question A. Okay, question B, what is the net charge? So we use Gauss's law. It says that the total flux is just equal to the charge enclosed divided by epsilon 0, which is 15 Newton meters per coulomb, we can get the charge enclosed is just equal to the flux, total flux times epsilon 0. And when you replace the values, you find that this is 1.33 10 to the minus 10, 1.33 10 to the minus 10 coulombs. Okay, could the net charge be a single point charge? Could the net charge be a single point charge? I don't think so. Why? Can it be a single point charge? Can it be one charge, 1 point charge? Yes. You raised your hand. يلا شباب. Yes. Because? Exactly. Remind you of your name, please. Okay, so thank you. Now, if we had one charge, it's going to be either positive or negative. So if we have a positive charge, all the electric field will be pointing away. And if we have a negative charge, all the electric field will be pointing towards the cube. The fact that we have, for some areas it's away and some areas towards, that means we have more than one charge. Some of them are positive and some negative. Depending on how close they are to the surface, you find the electric field. But actually, it's going to be difficult to find a uniform electric field in this case. So actually, yes, we cannot have a single charge, that's for sure. But certainly we will not be able to have just point charges, because if you have just point charges, I don't think you can get a uniform electric field on each of the surfaces. It's going to be very difficult to distribute all of these positive and negative charges in such a way you get uniform electric field on each of the surfaces. Well, practically it's going to be very, very difficult. Next problem. Okay, I think we have time for another problem, maybe. Okay, so 2 minutes for this one. So let me read it. The square surface shown measures 3.2 millimeters squared. So the area is 3.2 millimeters squared on each side. Okay? Okay, so it is immersed in a uniform electric field with magnitude of 1800 newtons per coulomb, with the field lines at an angle of 35 degrees. So this angle here, notice the electric field is piercing into the surface. This angle is 35 degrees with a normal to the surface as shown. This is the normal to the surface. This is the area vector. Okay? Now, take the normal to be directed outward. So this is directed outward, all right, as shown, as through the surface where on the face of a box. Calculate the electric flux through the surface. So we want to determine what is the electric flux. 1 minute for this one. This is easy. 1 minute. So calculate the flux. You are given the electric field. You're given the angle theta is 35 degrees, and you have the area or the side of the is 3.2 millimeters squared. 3.2 millimeters. Sorry, the side is 3.2 millimeters. Okay, so choose between A, B, C, or D. Okay, A, B, C, or D. I will start the Kahoot. Okay, 9 correct answers, and we have 14, 17 incorrect answers. So this was a little bit challenging. Okay, let's see who's the winner. So yeah, still 58381 is the winner, he or she. Okay, so let's see of this. What is this one? Okay, so here let's indicate clearly the vectors. All right, so this is the electric field vector. It's piercing into the surface. This is the area vector, so this is the delta A, the vector. Okay, and we have the flux. In this case, we can use the definition of the flux. We said it's E dotted with the area vector, delta A. Okay, the dot product, that means we can use E times delta A, cosine the angle between them, cosine alpha, I will call it alpha. Why I did not use theta? Because the angle is this angle actually. So if this is the area vector here, delta A, this is the electric field vector, this is the angle between them, alpha. Oh, since this angle is theta is 35 degrees, what is alpha? Alpha is 180 minus 35, which is 145 degrees. 145 degrees. So this is going to be E, which is 1800 times delta A. Delta A is 3.2 10 to the minus 3 squared times cosine of 145. When you calculate this, you find this is minus 1.5 10 to the minus 2 Newton meter squared per coulomb. So here the trick is determining the correct angle between the electric field vector and between the area vector. The angle in this case is 145, cosine 145 is negative. Okay, so you have to be careful. So I will stop here, and so